Next, we are going to talk about the reactions of nitriles. Now, nitriles can undergo hydrolysis. And when nitriles undergo hydrolysis, they are converted, the nitrile is converted into either the amide or the carboxylic acid. Now, the hydrolysis of nitriles can be affected or can be achieved using acidic or basic conditions again. Under acidic conditions, the nitrile in presence of acid and heat is first converted into an amide, and it would be a primary amide. Okay, it's converted into the primary amide, which can undergo further hydrolysis to the carboxylic acid and the ammonium salt. Now, whether you get the amide or the carboxylic acid as the product from this hydrolysis reaction really depends on the strength of the acid, like how strong of an acid you're using, and on the temperature. When the conditions are mild, that means you're using mild acid, low temperatures, then the reaction usually stops, or you're able to stop it at the amide. But if you're using forcing conditions, strong acid, high temperatures, then the amide is further hydrolyzed to the carboxylic acid under these conditions. Let's look at the mechanism for the hydrolysis of the nitrile into the amide. The mechanism for an amide hydrolysis to the carboxylic acid is the same as we've previously seen for the hydrolysis of an amide under acidic conditions. So under acidic conditions, the hydrolysis of a nitrile under acidic conditions, it bears some resemblance to the reactions of carboxylic acid derivatives under acidic conditions. So the first step under these conditions is a protonation or a proton transfer. So the nitrile nitrogen here, it gets protonated under these conditions. And it's going to give us the protonated nitrile. It will give us the protonated nitrile here. There's a triple bond here. And once this protonated nitrile is formed, along with this, we also have water here. And plus, this is a hydrolysis reaction, so there is enough water around. What happens is the water can now go and attack the nitrile carbon. And as that happens, this double bond opens, the triple bond, sorry, opens up to become a lone pair on the nitrogen atom. So that's now bring us to a RC double bond NH, one lone pair with the water now connected to that carbon with a formal charge on that oxygen. And since we are operating under aqueous conditions, from here, another molecule of water can deprotonate the species to put the electrons on that oxygen, which would give us the double bond NH, lone pair on the nitrogen with an oxygen, two lone pairs on that oxygen. So we get to a species. Now we are really close to becoming an amide over here because, again, under acidic conditions, what happens to the species is that this species can undergo protonation. And the nitrogen is what can get protonated, or when the nitrogen gets protonated, that takes us forward. So we make the next species where we have double bond NH2 with a formal charge and an oxygen, hydrogen with two lone pairs on it. And this protonated species, okay, and along with water that's formed as the side product, this protonated species here can undergo resonance. The oxygen can use its lone pair to do resonance, and that would bring us to NH2, lone pair, double bond, oxygen, hydrogen, one lone pair with a positive charge. So notice how we got the conjugate acid of an amide here. This is a protonated amide. And so finally, the water molecule here can do an acid-base reaction. So this was just resonance, and it would bring us to the amide in the end, along with a hydronium ion. So like every other reaction of carboxylic acid derivatives under acidic conditions, this hydrolysis only needs a catalytic amount of acid. And the amide that's formed here, which is the intermediate, under forcing conditions, if you heat it high or if you're using really strong acid, then this amide can undergo further hydrolysis to become the carboxylic acid. The mechanism of that step was discussed in a previous video that dealt with the reaction of amides, specifically the hydrolysis of amides. So please refer to that video for the mechanism of an amide hydrolysis to the carboxylic acid. Next, we're going to look at the hydrolysis of a nitrile under basic conditions. So under basic conditions, a nitrile can again be hydrolyzed to the primary amide initially, and then all the way to a carboxylic acid. Now, the mechanism of an amide hydrolysis to the carboxylic acid under basic condition was previously covered under the reactions of amides. What we're going to do here is we're going to look at the mechanism of a nitrile's hydrolysis to an amide under basic conditions. And again, the nature of the product or the extent of hydrolysis here would depend on your conditions. If you're using lower temperatures, then your nitrile would be hydrolyzed only as far as the amide. But if you're using higher temperatures, then the amide would undergo further hydrolysis to the carboxylate, which after an acidic reaction, an acidic workup, can be converted into the carboxylic acid. So that's something that was common to the basic hydrolysis of amides also. When we did the basic hydrolysis of amides, we first reacted with base and then did an acidic workup to convert the carboxylate into the carboxylic acid. Like I said before, let's look at the mechanism of how is a nitrile converted into the primary amide under basic conditions. So the reaction here, similar to reactions of other carboxylic acid derivatives under basic conditions. So I'm using aqueous base here, so that's why we have hydroxide and we have water. The hydroxide could be sodium hydroxide. So under these conditions, the first step is the attack by the hydroxide on the nitrile carbon. Notice this is similar to the reaction of other carboxylic acid derivatives under basic conditions, where the nucleophile goes and attacks the acyl carbon. So it's not the acyl carbon here, but the nitrile carbon is what gets attacked. And simultaneously, one of the pi bonds is going to open up. This is going to bring us to the next intermediate, where we have a double bond between that nitrogen and the carbon, the nitrile nitrogen and the carbon. And this carbon has a hydroxyl group connected to it or bonded with it. And this nitrogen here does not have a hydrogen, but it should have a negative charge on it. And then under aqueous conditions, this nitrogen can now get protonated using water. And as you can see, that protonation is going to generate more hydroxide. We used a hydroxide in the first step, and in the second step, we're going to generate more hydroxide. So we get RC double bond N, H, one lone pair, and we have the hydroxyl group here. Plus, we've generated hydroxide ion. So we get the hydroxide ion. And now from this intermediate, the hydroxide base that's formed, this reaction is going on under basic conditions, can deprotonate this hydroxyl group, And the electrons from this bond can basically end up on that oxygen. Yeah, let's show it step by step. So it can end up on that oxygen. So this is going to bring us to RC double bond NH, one lone pair, oxygen with a negative charge plus water. So we get the water back, and we've gotten what is actually the conjugate base of an amide. Doesn't look like the conjugate base of an amide, but once you do resonance on this species, let's do resonance here, we will get RC single bond NH, negative charge, and double bond O with two lone pairs on it. Now notice this is the conjugate base of an amide, which in the final step can undergo protonation, can do a proton transfer from water. We are under aqueous conditions here to give us finally the amide molecule. So we get the NH2, and plus we're going to get the hydroxide back. So notice how this reaction is only base catalyzed, this step. We started with the hydroxide and we got the hydroxide back in the end, and in the process we've converted this nitrile into a primary amide. And once this amide is formed, the mechanism of how the amide becomes the carboxylate and then later becomes a carboxylic acid, that was discussed in a previous video dealing with the reactions of amides. Next, we're going to look at the reaction of nitriles with Grignard reagents. Grignard reagents, as we know, are strong carbon nucleophiles. So when a nitrile reacts with a Grignard reagent, okay, what happens is that the nitrile here is converted into a ketone. Okay, that's the product from this reaction. Like all other Grignard reactions, the first step is the attack by the Grignard, which is followed by a hydrolysis. But the end product that we get is a ketone. So let's look at the mechanism of this reaction, how this happens. Okay. Now, like any other reaction involving the nitrile or Grignard, which is a strong nucleophile, the first step here is going to be the attack by the Grignard reagent on the nitrile carbon. And this would open up one of the pi bonds here. And that would bring us to this intermediate where we have the double bond to the nitrogen with two lone pairs on it, which would give it a formal negative charge. And the R prime here is connected to that carbon. What was the nitrile carbon? It has the R prime also connected to it. Now, at this point, we've created a species in which there is a nitrogen with one negative charge. And this negatively charged species might be balanced by the magnesium, which is positively charged. Now, since there is already one negative charge on this nitrogen, attacked by another Grignard on this carbon, to open up that pi bond, which would give a species with two negative charges on that nitrogen, is highly unlikely. So that process doesn't happen. And what happens is from here, you go into the second step, which is the hydration step. Okay, you're doing an acidic workup here. So this was the first step, which was the attack by the Grignard. The second step is the hydration. So what happens here is the nitrogen gets protonated under these conditions, and it would bring us to this species here where we have a nitrogen with a double bond to the carbon. Now, if you look at this intermediate, this is an imine, okay? And we are under acidic conditions. That means under these conditions, okay, and we are going to make water along with it. And so since we are under acidic conditions, there is enough acid present. The imine nitrogen here can get protonated again. Okay, it gets protonated again, and it would give us the protonated iminium ion. It would give us the iminium ion, and plus water. And since this is aqueous acid, under these conditions, the water molecule can go and attack this carbon. Now, we've seen this mechanism before, which is the hydrolysis of an imine to the carbonyl compound. So the water goes and attacks that iminium ion, and we are going to get RC R prime. We'll have NH2, and we'll have OH positive charge and one lone pair on it. We get that intermediate. And since the conditions here are aqueous, this intermediate can be deprotonated by water. Another molecule of water can come and deprotonate that intermediate, and that would take us forward to the next intermediate here, which will be NH2 with a hydroxyl group on that carbon plus H3O plus. And I'm going to write out that hydronium ion because we're going to use it in the next step of the mechanism here. So we get the hydronium ion. And from this intermediate here, either the hydroxyl or the amine can get protonated. The amine is more basic, more likely to get protonated. So when it gets protonated, it's going to move us forward. So we're going to get C.1R with an ammonium ion and a hydroxyl group in the same molecule. Now, this ammonium should be a good leaving group. We've converted that amine, which was a bad leaving group, into a good leaving group. And so the hydroxyl group can use its lone pair to help push out that nitrogen, make it help in the process. And so that would give us an RC R prime, double bond O, H, one lone pair, positive charge, along with ammonia, which just came out here. And because ammonia is a strong base, under these conditions, it can help deprotonate this intermediate here, the protonated carbonyl compound, the intermediate, which is a protonated carbonyl compound, and it would bring us to a ketone plus an ammonium ion. So that's how the nitrile ends up as a ketone under these conditions. Notice this is really not a reaction, it's just a workup. But the product that we make, the imine, under these acidic conditions, it is unstable, and so it undergoes a hydrolysis to give you the ketone and the ammonium ion. We've looked at this same mechanism earlier when we discussed imine hydrolysis. So that's the reaction of nitriles. We've talked about the hydrolysis of nitriles. We've also talked about their reaction with Grignard reagents.